All right, so in this bell work here, I kind of want to continue that idea of like, how do you determine if 3 points are collinear? So last time we talked in the last journal, we talked that when you have 3 points that are collinear, they form a straight line. Oops, sorry, that looks kind of ugly. So they are points that are on a single line, basically. And a line is one-dimensional, and we talked about how a one-dimensional object does not have an area, so the area is automatically 0. So the nice part here is that to figure out if something is collinear, well, all you have to do is use that formula to find the area of a triangle and see if the area gives you 0. Because if it does, that means there was no triangle and that there had to have been 3 points that formed a straight line. So let's go ahead and test that out here. So I'm going to start my area formula. And so that's where you had to have the x and y, your coordinates. So this is 6 and 8 for the first coordinate, 4 and 6, and then 2 and 4. It doesn't matter the order that you wrote your coordinates as long as your x's all line up and your y's all line up in the column that they're supposed to be in. And then the last column, remember, it's just a bunch of ones. And then you take your first 2 columns and you paste it over. So this will be 6, 4, 2, 8, 6, 4. And then what you're going to do is take the top left row, top left column and diagonally move downwards. Oops, that's not a highlighter. And multiply those numbers in that diagonal. So when I multiply the first set of numbers, 6 times 6 is 36. 8 times 1 times 2. Oh, sorry, that was not the right pen. 36. 8 times 1 times 2 is 16 for the next diagonal. 1 times 4 times 4 is 16. Now I'm going to bring down the plus and minus 1/2, and in brackets I'll show all my work for the determinant. So remember, determinant uses a minus sign, so I'm going to grab these numbers and stick it in here. So this is 36 plus 16 plus 16. And then this will be 2 times 6 times 1, 4 times 1 times 6, 1 times 4 times 8. So this will be a 12, 24, and 32. 12 plus 24 plus 32. And then looking at this, I have plus and minus 1/2. I'm going to add up all these numbers. So 36 plus 16 gives me 68 minus, if I add up all the green numbers, 12 plus 24 plus 32 gives me 68. Well, if they're going to both be 68 and I'm subtracting, that means that that's going to give me 0, right? So I'll bring everything down, but the bracket inside is going to be 0. And I would multiply this 0 by the number that's front, and then still be 0. So 100% sure this is going to definitely give me a 0 if the area is 0. So if the area is 0, that means that, yes, the points are collinear. So to check if points are collinear, use the area of the triangle formula and find out if the area is 0. If it is, then they are collinear, and you did make 3 points form into a straight line. All right, let's get into today's journal. When we multiply matrices, what we have to do is we always multiply the rows from the first matrix. We always take the rows, and we multiply it with the columns in the second matrix, right? Now, before we do this, let's figure out the dimensions. This one's just your simple 2 by 2, and so is this one. It's a 2 by 2. So the inners do match, and so if they're the same or if they match, then that means you can multiply. The outers tell you the shape that it will make, or the dimensions that your resulting matrix will be. So this will be a 2 by 2, since that's what the outer dimensions are. And so if it's a 2 by 2, I like to make like a grid, so that way I know that this is 2 rows and 2 columns, and I know where to put the numbers in when I multiply. So when I multiply here, let me use that. That looks like it will fit. All right, I'm grabbing my highlighter here. So I'm going to grab the first row from this column and multiply it by the first row in this. So the first row in this matrix and the first column in this matrix, and multiply. When you multiply, you're going to multiply the first number here with the first number here. So 5 times 3 gives me 15, and it's going to go in this box because this is the first row and first column, and you're multiplying the first row with the first column. Then you want to add it to the next two numbers you multiply. So 7 times -2 is -4. Next, I'm going to multiply the second column to get the number that goes in the second column in the top. So 5 times -7 gives me -14, plus 7 times 5 gives me 35. And then the bottom here, I have 2, 3 times 3, -2. So when you multiply, this is the second row. So you're in the second row, first column. So this goes in this box. So 2 times 3 is 6, plus -2 times 3 gives me -6. And then in this one here, we have, oh, I just noticed something. I think I messed up here. Yes, I did. So it looks like I messed up. 5 times -7 does not give me -14. I don't know where I got this -14. 5 times 7 gives me -35. Okay, I fixed that. My bad. And then, so I'm going back to this one now. So this is the second row, second column. So I'm going to multiply the second row with the second column. So 2 times -7 is -14, plus 3 times 5 is 15. All right, let's clean it up here. So again, this is going to be a 2 by 2. In the first box here, 15 plus -4, so 15 plus -14 is 1. Next number, -35 plus 35 is 0. The second row, these two will combine to give you 0 as well. And then the last box here, -14 plus 15 gives me 1. And so here is my new matrix. Now I just want to go over something special about this matrix. This type of matrix here is what we call the identity matrix, and it's specifically for a 2 by 2. The identity matrix is where you have like a diagonal of 1s and the rest of the numbers are 0s. So like an example of a 3 by 3 identity would be 1, 1, 1, and then the 0s would fill up the rest of it. So this would be a 3 by 3 identity matrix. So identity matrix act like 1, like the number 1. When you multiply by an identity matrix, you get the same matrix back. In other words, if I multiply this first matrix with the identity matrix, I'm going to get back this matrix here. So another thing that I want to mention is that anytime you multiply two matrices together and they give you the identity matrix, that means that they had to have been inverses of each other. So in conclusion, this product or this multiplication tells me that the two matrices are inverses or inverses of each other. So that's one way you can check if something is inverses of each other, is to multiply, and if you get the identity matrix, and that's kind of clarifies or confirms that they are inverses of each other. All right, let's go into like what does it mean to be an inverse and that. So there is a formula to help you find the inverse, and in Algebra 3, I'm only going to teach you how to find the inverse of a 2 by 2. A 3 by 3 is requires more complicated skill, so we're going to keep it real simple since we're still in high school. So first off, if you have a 2 by 2, I'm going to use something very generic. So I just put some A, B, and C, and D in here. Basically, this is the inverse formula. So let's just walk us through this here. So there's a 1 divided by this A, and notice this A is in absolute, like these lines besides the A. So A was this matrix, this 2 by 2 matrix. So it says you need to find the determinant, because those straight lines mean determinant, of A. So this guy right here is the determinant. So you found the determinant, and the determinant is just some number. And then notice that this here looks awfully like this guy. The only thing is that basically A and D, let me use a thicker, A and D are like A and D here, but they're switched. So the first diagonal gets switched places. So switch places. The second diagonal basically change signs, right? So this was C and B. Notice how this C and B has a negative sign, or in other words, they will flip signs or switch signs, and that's it. So they don't switch places, they just switch signs. So you're going to get some number that's a determinant, and it's outside of the matrix. You're going to do some switching here, whether it's switching places or switching signs. And then you're going to be able to find the inverse matrix. All right, so let's do some practice problem here. Okay, so in this matrix here, we're going to do number 11. And to find the inverse, I'm going to need to first grab that formula that I had. So I'm going to write it up here so that way we can see it together. So this inverse matrix is 1 over the determinant of A. And A is just that 2 by 2 matrix. And then remember, we're going to have to switch the matrix, the first diagonal. And so let me use my highlight here. So these two get switched. They just switch places. And then the other diagonal, C and B is what I think I called them. They just switch signs. So I'm just gonna, I keep not touching my highlighter. There we go. So they switch signs. Let's write that in. All right, so there's our formula. Let's go ahead and find the inverse. So the inverse of this, I'll just write inverse of A, we'll just call this matrix A, is 1 over the determinant. So the determinant, we talked about this last time, you always take the diagonal, so you're going to multiply the first diagonal, so -1 times 4 gives us -4, minus the other diagonal, which is -2 times 3, which gives us -6. And then I already spot that there's 2 negatives, so we might have to change that. And then we are going to do our switching of our matrix. So again, remember these two numbers in this diagonal will switch places. So now this is a 4, and that's a -1. Whereas the other diagonal switch signs. So this is a -3, that's a +2 now. And so let's clean this up. So the bottom here will become plus sign. So if I add up those numbers there, that's 1 over 2, right? -4 plus 6 is 2. And so I have a 1/2 in front of my matrix. I'll bring down the matrix here. So it looks like I'm distributing a 1/2 into this matrix. Remember, this number here is just your scalar, and you multiply it into everything in the matrix. So 1/2 times 4 is 4 over 2. Basically, I just like mentally put that over 1 and then multiply straight across, right? Because 1 times 4 is 4. 2 times 1 is 2. Then I'm going to multiply 1/2 with 2, so that'd be 2 over 2. And then 1/2 times -3 is -3 over 2. 1/2 times -1 is -1/2. And then if I were to just clean this up just a little bit, I can see that the top number here, 4 over 2, is just 2. 2 over 2 is 1. -3 over 2 is, I'll just keep it as a fraction because that doesn't reduce. And then the bottom one's -1 over 2. So looking at this here, it looks like this is my inverse matrix. So basically what this is like if I were to multiply this matrix with this matrix, I would get that identity matrix again, is what's supposed to happen. All right, let's try it out with 13 here to see if we can find the inverse. So again, remember we're going to use that formula. Then start with our inverse here and find our determinant. So I'm just setting things up here. So I'm going to take this first diagonal, multiply that. So that's 5 times negative 6, which is negative 30, minus the other diagonal. If I multiply negative 3 times 10 is also negative 30, right? And then what I would do is you always switch places with the first diagonal. So that becomes a 6, negative 6, and that becomes a 5. You don't switch the signs, you just switch the numbers. And then the other diagonals, you are going to switch the sign. So this will become a positive 3. This will become a negative 10. And then the bottom here, because I noticed this will be a plus sign, that's going to be 1 over negative 30 plus 30 is 0. And then I'll bring down the other matrix. But hold up there. You guys probably already spotted. There is a 0 in the denominator. And last time we learned about zeros in the denominator, we can't have that, right? If you have a 0 in the denominator, this is undefined. So because that's undefined, that means that this matrix is undefined. So basically, let's write this in, the inverse matrix doesn't exist. Or you can say that the inverse matrix is undefined. Because when you were finding the determinant, it caused you to have a 0 for your determinant, which caused the overall fraction to be undefined. All right, so this one's just not solvable. It happens. Okay, so now that we've had some practice, I want you to try your own exit ticket problem in the next slide here. So here is the exit ticket problem. You're going to find the inverse of this matrix. So go ahead and use that formula that was in the previous slide to help you out here. And if you get this problem right, let me know in class and I will give you a stamp. All right, have a great day, guys. Bye.